Hi, today we're gonna deal with topological and algebraic properties of the spectrum of a ring. So let's start with a definition. So we let A be a ring, and as usual commutative with 1, and Y be a subset of the spectrum of A, so that's a set of prime ideals as we have seen. And now we define this ideal of Y. So you might know an analogon of this from classical algebraic geometry, but if you don't know it, it's not well. We you'll see it now in the modern setting, so that's okay. Okay, so that's our first definition. It's just the intersection of all the prime ideals contained in Y, and then we take the intersection over these prime ideals. Now let's make a second definition. So let's take an ideal in A. Be an ideal, so you know what I want to say. And now we define the radical of this ideal. We might denote it with this symbol, which you know from the square root, or we also just write radical. And please don't confuse it with the Jacobson radical. That's something different. It can coincide, but in general it doesn't. So let's define it. So that's the set of elements in the ring such that, let me write it differently, such that f to the n is an A for some integer bigger than 0. Okay, so that's that definition. Also note that this is the intersection of the prime ideals such that A is a subset of P. You can prove this using Zorn's lemma, but we won't prove it here, but we'll use it later. And let me see, do I want to say more? I want to say one more thing, namely we call an ideal radical if, let's call this ideal A, if A is just equal to its radical. Okay, I think that's it for the definitions for now. Now let's get into the properties of the ring and algebraic properties, and then topological properties of the spectrum. And now that I say that's it, one more remark, namely if we so we have this I of Y, and so as we had also for the V, so for the vanishing, also for this I of Y, we get that this is inclusion reversing. So if we take a subset of Y, then we have an intersection over less ideals, so it's a bigger set. So that's inclusion reversing. Okay, now let's prove a proposition. Namely, the first thing we're gonna prove is that the radical of I of Y, so Y again being a subset of the spectrum, is equal to I of Y. So this ideal of Y is radical. That's the statement. The next thing we'll see is that if we take the ideal of the vanishing of A, this is equal to the radical of A. And furthermore, that if we do it the other way round, then we get the closure in the spectrum of A. And then the third statement is, so now we have maps, namely radical ideals, A in A, and we get a map to, well, there's a little bit, it's not much space, but Y subset spec A closed. And on the one hand, so that's just the vanishing, and then we get a map in the other direction, namely Y gets mapped to I of Y, and these maps are inverse bijections, so that's quite easy to see from 2. And also prime ideals correspond to irreducible subset. I'm not sure if we defined what irreducible is, so let me mention it when we actually prove it. So under these maps. Okay, so that's the plan for today. And now let's prove it. Let's start with the first part. So the first part, so it's quite clear. Let's look at the definition of the radical again. So that's just a set of elements such that f to the n is an A for some n bigger than 0. So if we take n to be 1, then we get that A is a subset of the radical. And let me also note that the radical is an ideal again. You can check this. But now let's see. So we definitely see that the ideal, for any ideal A, it's contained in the radical of A. Okay, so now let's take f in the radical of I of y. So what does this mean? Well, f to the n is an I of y for some n. Now let's look at the definition. That's the prime ideals in y, so the intersection. And well, now we see, so f to the n is in all these prime ideals. Well, since these are prime ideals, it means that f is in all these prime ideals. So that means that f is an I of y. Okay, and that's, so we have that if it's in the radical, it's already in the ideal itself, and the other inclusion is clear. So that's part 1. Let's look at part 2. So we want to prove that I of v of a is equal to the radical of a. So let's see this. So let's look at I of v of a. So that's the intersection of the prime ideals in v of a and p. And well, that's the intersection. So p is in v of a. So that's the prime ideals such that A is a subset of P. And now let's look again. So here we had, let me use another color. Let's look at this. So that's just the radical of A by its own lemma, as I mentioned before. So that's that. So we've done with that part. Now, next thing we want to prove is that v of I of y is the closure of y in the spectrum. So let's see. So if we have let's look a little bit more general. So if we have y in a closed subset, so in some v of a, so that means that that's the p such that a is a subset of p, and so that means that p in y, so let me maybe state it. So this statement is equivalent to the statement p in y implies a subset p. And well, that statement is equivalent to a is a subset of the p and y p, which is I of y. So we get that y is a subset of v of a if and only if a is a subset of I of y. Okay, and now we use the property that I of y is inclusion reversing and v of a is inclusion reversing. So if we want to get the minimal a such that y is a subset of v of a, we have to take the maximal a here, and the maximal a is I of y. So we get that y bar is just v of I of y. Okay, that's that. Okay, so the next statement, so let me also make dots here. So the first dot of 3 follows immediately from part 2. So if we have a radical idea, we get a closed subset, and then so this is clearly a rejection if we look at these things here. But you might want to check this a little bit more carefully if you doubt it. Okay, and now let's move on to the last part, namely that prime ideals correspond to, well, irreducible closed subset, I should mention. Well, definitely we have closed already here, but let me stress it again. Okay, now let me tell you at first what a irreducible space is. So a topological space X is called irreducible if, let's say, X is equal to V1 union V2 for some closed subsets V1 and V2, that this implies V1 equal to X or V2 equal to X. And note, there's this kind of similarity to connectedness, and namely we can see easily that if a space is irreducible, it's also connected. The inverse implication is not true in general, but there are also other characterizations of irreducibility of a space, and you might want to look them up. They can sometimes be very helpful. Okay, but for now we just need this, and we'll stick with that definition. So let's take a prime ideal, let P be prime, and now assume that V of P, so we know what the closed subsets in the Zariski topology, so we can just assume that it's some V of A1 union V of A2. And now we want to prove that one of these sets is already the whole space. Okay, so that's that. Then from previous parts, we know that P is equal to the radical of A1 times A2. Okay, we also know now that A1 times A2 is a subset of P, and then we get that A1 is a subset of P, or A2 is a subset of P. So if not, then we can take from both sets element, multiply them together, and they are in P, and both are not in P. That's a contradiction to P being a prime ideal. So that's that, and so we have A1 subset of P, and then we get that V of P is a subset of V of A1, which implies that V of P is actually V of A1, which we wanted to prove. So, let's say here without loss of generality. So V of P could of course also be a subset of A2 if we're in this case. But we're in one of these cases, so we have that the space is irreducible, and if P is a prime, and now let's prove the other direction. So let me maybe make something so we know what did I start with primes in the statement? Yeah, prime ideals correspond. Okay, and now let's prove the other direction. So let's take a closed irreducible subset. So let V of A be irreducible. And we want to prove that with A radical ideal, and we want to prove that A is indeed a prime ideal. Okay, so let's assume A is not prime. So assume A is not prime. So, actually, I don't think we need to assume it. Let's see if we need it, but I think we don't need a contradiction. So let's start with let's call it B and C, not A and B. Let B times C be an A. Okay, what do we get from here? Well, we get that V of A is a subset of V of the ideal generated by A times B. And that's V of, I wanted to call it B and C, sorry. B times C. So V of B union V C. And so that's that. Okay, and from here we get that V of A is equal to V of A intersection V of B union with V of A intersection V of C. And okay, so that's that. And now we get by irreducibility that without loss of generality, V of A intersection V of B is equal to V of A. And well, that's V of A union with the ideal generated by B. And well, now we have previously we've seen where do we have it? We've seen this bijection here, and we know that if let me go back again. So if this would be a set greater than B and A is red, so if let's say A, so A is a proper subset of this, then we would get by the previous part that this couldn't be equal to V of A. So that means, so that would imply that V of A union B is not equal to V of A. And so we get that B is a subset of A, which means that B is an A, which means that A is a prime idea. Okay, yeah, so that's what we wanted to prove. That's it for today. Let's see, maybe, yeah, I will definitely deal a little bit more with the topology of the spectrum, because we want to look at a special basis of the topology in order to define the structure sheaf later. Okay, yeah, that's it. Have a good day and bye.